Hi there, this video is on section 1.5, one-to-one functions and inverse functions. So first we're going to talk about the definition of a one-to-one function. And you guys remember we've talked in previous sections about the definition of a function, right? For something to be a function, every element in the domain must correspond to exactly one element in the range. Well, for a function to be a specific type of function, we call it one-to-one function, every element in the domain must correspond to exactly one element in the range, but also every element in the range must correspond to exactly one element in the domain. So basically, every x must correspond to exactly one y, and every y must correspond to exactly one x for a function to be a one-to-one function. It can still be a function without being a one-to-one function. Now, for what I have written here, I also include this part. This is from your text, where basically if A is not equal to B, then f of A is not equal to f of B. And that just says that if you have two different x values in the domain, then their y values cannot be equal to each other, right? Every x must correspond to exactly one y. Every y must correspond to exactly one x to be one-to-one. For a graph to represent a function, it has to pass the vertical line test, and that falls back on the definition of a function. For a graph to represent a one-to-one function, it has to pass what we call the horizontal line test. And the horizontal line test just also falls back on the definition of a one-to-one function. But basically, the horizontal line test says that if you have the graph of a function, so it's already passing vertical line test, but if you were to draw a horizontal line anywhere and it were to intersect the graph at more than one point, then the graph would fail the horizontal line test and not be a one-to-one function, because there would be multiple y values that would correspond, there would be a y value that would correspond to multiple x values, and that's not a one-to-one function. To help me keep it straight, I always think about y equals to x squared as my example of a function that is not a one-to-one function, at least not over its implicit domain. So if we think about the graph of x squared, so y equals to x squared, right? There's infinitely many horizontal lines that we could draw that would end up intersecting the graph at more than one point. Now, if we drew a horizontal line at y equals to 0, yes, it only intersects at one point, but it's because there are horizontal lines that we could draw that would end up intersecting at multiple points, that this graph fails the horizontal line test, right? If we thought about this point as being the point, let's say 2, 4, and this point being negative 2, 4, oops, right? That y value 4 ends up corresponding to two different x values. So y equals to x squared fails the horizontal line test and is therefore not a one-to-one function. However, if we were to restrict the implicit domain of y equals to x squared, we could force y equals to x squared to be one-to-one. So how about y equals to x squared for x greater than or equal to 0? Well, that graph would pass the horizontal line test, right? Any horizontal line you could think of drawing would just intersect the graph at exactly one point. So since that horizontal line test passes, therefore that function is one-to-one. Oops. So give an example, example one-to-one function versus not one-to-one function. Give an example of a function that would pass the horizontal line test and an example of a function that would not pass the horizontal line test. So I just gave one above. Why don't you maybe pause this video and think for a sec. about a function that would not pass the horizontal line test and therefore not be one-to-one, and then also a function that would pass the horizontal line test and would therefore be a one-to-one function. So there's lots of different ones. Pause the video, try it. I'm going to do absolute value of x for not passing the horizontal line test. So it fails the horizontal line test. This is for y equals to absolute value of x. Fails the horizontal line test. And is therefore not a one-to-one function. A function that would pass the horizontal line test would be like square root of x. So y equals to the square root of x would pass the horizontal line test and therefore is a one-to-one function. So let's talk about determining algebraically if a function is one-to-one or not. And it just uses the definition of a one-to-one function. So basically it says that if f of a is equal to f of b, so basically if you have two y values equal to each other, well, the x values that they correspond to must also be equal to each other. And you should be able to uncover that algebraically if the function is in fact a one-to-one function. So the way that we do that, I'll give you an example with f of x equals to 2x cubed minus 7. Now I know the parent function x cubed would pass the horizontal line test and therefore be one-to-one. And vertically stretching by 2, shifting down 7, that's not going to change that. But the way that we would show this algebraically is we want to know if we were to evaluate the function at, say, a and b, the a is equal to b. So if I did 2a cubed minus 7, is that equal, put the question mark over the equal, is that equal to 2b cubed minus 7? Now, if we can uncover and get down to a equals to b, then the function will be one-to-one. So this is a proof, right? We're showing that a is equal to b, so we should be showing all of our steps. I'm going to first think about adding 7 to both sides of this equation that's using the addition property of equality. And then that leaves us with 2a cubed on the left side and b cubed on the right side. If we divide by 2 on each side, it's using the multiplication property of equality, then we'll have a cubed on the left and b cubed on the right. And if we thought about raising both sides to the 1/3 power, which is the same as taking the cube root, we would end up with a equals to b. Okay, that works. Therefore, f of x is one-to-one. We've shown that algebraically. Okay, well, x squared minus 3, we just talked about how x squared over its implicit domain of all real numbers does not passed the horizontal line test and is therefore not 1-to-1. So let's look at what happens algebraically when we try to see if x squared minus 3 is 1-to-1. So we would have a squared minus 3 on the left, b squared minus 3 on the right. We think about adding 3 to both sides. And then we have a squared on the left, b squared on the right. Well, couldn't a be a positive or a negative value from here? And b could be also a positive or negative value. So those values, a and b, don't necessarily have to be equal to each other, meaning that those output values, those y values, could end up corresponding to multiple x values. So therefore, f is not 1-to-1. Okay, another function that we know is not 1-to-1. I want to show you what happens here. So if we have absolute value of a minus 2 on the left, absolute value of b minus 2 on the right, well, whatever's inside the absolute value bars could be positive or negative, because when you take the absolute value, that represents the distance of whatever is in the absolute value bars from 0. So like a minus 2, that quantity could be positive or negative. And then the same thing as what happens above happens like b minus 2, that quantity could be positive or negative, right? So you could end up with, let's say, a minus 2 equals to positive b minus 2, or you could end up with a minus 2 equals to negative b minus 2, where those wouldn't be equal to each other. So therefore, f is not 1-to-1. But why do we care about whether a function is 1-to-1 or not? Because we care about inverse functions. They're going to be really useful for us. So an inverse function is a function that reverses another function. So if f is a function mapping x to y, then its inverse function maps y back to x. I've given you a little picture there. What I always like to do is draw the little function machine like they do in Algebra 1. So like let's say that we have our function machine f. And if we think about inputting, let's say 2 into our function, it spits out 7. Well, if you then took 7 and input it into f inverse, the inverse function of f, it would spit 2 back out. So two functions that are inverses of each other, their domain and ranges switch. They flip-flop, right? Because the inputs of the one function will be the outputs of its inverse. And the outputs of the function will be the inputs of its inverse. So to algebraically verify that two functions are inverses of each other, we compose them both ways to make sure that the output of the outer function being evaluated by the range of the inner function is the domain of the inner function. So basically, in order to verify that two functions are actually inverses of each other, you compose both ways. F composed with G, G composed with F, and make sure that the equation simplifies down to X for over the domain of the inner function, right? Because you're thinking about evaluating the outer function at the range of the inner function. And then that needs to map back to the domain of the inner function. And then I put a note on here. F inverse we use it to denote the inverse function. The superscript -1 is not an exponent here. So basically, this is not 1 over f of x. It's not the reciprocal. It's f. It indicates the inverse function, which gets especially tricky with one of the notations that we use for like the inverse trig functions. But we'll talk about that later on this year. So let's practice verifying the two functions are inverses of each other. So 3x plus 2, f of x equals to 3x plus 2, and g of x equals to x, the quantity x minus 2 divided by 3. Well, both of those functions have implicit domains of all real numbers. So this needs to be true over all real numbers, composing both of those. So f composed with g, let's start with that. Okay, so that would be f is the outside function, g is the inside function. Okay, and then I should have given myself more, or I can do it this way. I can do vertical steps. Okay, those 3's will be able to cancel. And we'll have x minus 2 plus 2, which is equal to x, and that's over all real numbers. So I can say x is an element of the real numbers. Okay, and then let's also show g composed with f. It has to work both ways for them to be inverses. So that's g is the outside function, f is the inside. Okay, so I can drop those parentheses in the numerator and then the 2's would cancel. That leaves me with 3x over 3, and then the 3's can cancel to be x, and that's also true over all real numbers. So I can say x is an element of the real numbers. Okay, so we have verified that f and g are inverses of each other. So we can say something like, therefore, f and g are inverses of each other. Okay, so notice we have a domain restriction for one of the functions here. So remember, it's for the domain restriction of the inside function. So let's verify that f and g are inverses of each other. Let's first do f composed with g. So g is the inside function. And so this should be true for x greater than or equal to 0. So thinking about distributing that negative, those 2's can cancel, so we'll have the square root of x squared, which we can simplify down for x. But over all real numbers, this would actually simplify to be absolute value of x, right? Because x could be positive or negative since it's being squared. But this is true for x greater than or equal to 0. That's important. And let's do g composed with f. This will be for the domain of the inside function. So we'll have 2 minus the square root of 2 minus x squared. So that'll end up simplifying down to 2 minus the quantity 2 minus x. And then if we distribute that negative, that simplifies down to x. This will be for the domain of the inside function, which if we think about the fact that 2 minus x would have to be greater than or equal to 0. Switch that around. So that's for x less than or equal to 2. Okay, and that would be true. And therefore, f and g are inverses. So ditto from up above. Okay, the graphs, this is kind of cool. The graphs of inverse functions. So the graphs of two functions that are inverses of each other are reflections of each other over the line y equals to x. And that should make sense. The fact that the two functions that are inverses of each other, their domains and their ranges just flip-flop. So like all of the x values and all of the y values just switch. And therefore, the graph ends up being symmetric about the line y equals to x. So in other words, if the point b comma a lies on the inverse function, then the point a comma b would lie on the function f. So like if we were to, I don't know, if I drew a one-to-one function, so something like, let's do just like a shifted parabola. And do these points. Okay, I'm picking 3 points there. So let's say that this was the graph of f, and I see we have point 0, 2, negative 1, 3, and negative 2, 5. Well, now I can figure out what the graph of its inverse looks like, right? 2, 0. 3, negative 1, and 5, negative 2. Kind of cool. So here's another example. So this is a sketch of the function f of x in red. So that's f of x. And we want to find the graph or sketch the graph of f inverse. So to do that, I'm going to pick some points. I'm going to use green. I'm going to pick some points that I see on f. So I see the point 0, 5. How about 2, 0? And 4, negative 3. Okay, so now I can just switch the x and y. So 5, 0. Maybe I'll use another color. 5, 0, 0, 2, and then negative 3, 4. So that would be f inverse. Now we keep falling back on the definition of an inverse function, right? Domain and range flip-flops for two functions that are inverses of each other. So for finding the equation of an inverse function, if you know that a function is one-to-one, that's kind of your first step, right? You need to make sure that the function is one-to-one. It can also be super helpful to state the domain and range of the function for reference, because you know that the domain and the range are going to switch, especially if the inverse is a function that has to have its domain restricted to be one-to-one, right? Because if a function's an inverse, that means that that function also has to be one-to-one because it has an inverse. So you switch the x and the y in the equation, and then you solve for y in terms of x, and then you can rename y f inverse or g inverse or whatever it is if you're using function notation. And then you want to make sure you state domain restrictions if it's needed. I think it's always a good idea for inverses to think about the domain and range because it's just so important. But you should know based on thinking about the domain and the range of the given function. So let's work through some of these. So we're going to find the inverse of x cubed minus 1. Now we know that this graph would pass the horizontal line test. You can visualize, so we know horizontal line test passes, therefore 1 to 1. So we can move forward, and I'm going to switch f of x to be y. And just thinking about domain and range are both going to be all real numbers for f. Therefore, the domain and range of its inverse will also be all real numbers. Okay, so switching x and y, here I'll switch colors. Switching x and y, we can now solve for y in terms of x. So if I add 1 to both sides of the equation, and then we can, to isolate y, take the cube root. So f inverse would be the cube root of x plus 1 over all real numbers. So domain and range would be all real numbers. Okay, so let's try this square root function. Would pass the horizontal line test. It's okay to do kind of a mental check, right? Therefore, 1 to 1. Domain, we would need to think about x minus 1 being greater than or equal to 0. So x would be greater than or equal to 1. That would be 1 to infinity in interval notation. And then the range, well, this is the square root of x as the parent function. That minus 1 is shifting to the right 1, so it's not doing anything to the range because there's no vertical shift. And the range of the square root of x would be 0 to infinity. Okay, so that's just thinking about the graph of the square root of x minus 1. Okay, so let's switch x and y. So we'll have, here I'll move over here, x equals to the square root of y minus 1. And we need to isolate y. So we'll think about squaring both sides because we have no other strategy to use. Oops. And then we can add 1. Well, hold on, x squared plus 1 would not pass the horizontal line test, but remember, we do know what the domain restriction is to force it to be 1 to 1. So we can say that f inverse would be x squared plus 1, comma, referencing the range, which will now be the domain of f inverse, x greater than or equal to 0. Okay, so that buddied with it is important. We are explicitly stating the domain here because the implicit domain has been restricted, like it has to be. If it wasn't stated, your answer would be wrong. And the domain and range switch. So domain, just restating it again in interval notation. Range would be from 1 to infinity. Which makes sense, right? For x squared plus 1, x squared shifted up 1. Okay, so let's do for this rational function, 1 over x minus 2. Parent function is 1 over x. So the 1 over x shifted right 2. That would pass the horizontal line test. and therefore is a 1-to-1. Okay, domain would be all real numbers except for 2. Right, we can easily see that 2 would make the denominator 0. Or you could think about the fact that there was a horizontal shift to the right 2 for 1 over x that shifts the vertical asymptote over 2 units. And then the range, thinking about the graph of 1 over x, has not been vertically shifted. We'll have a range from negative infinity to 0, union 0 to infinity. So then we're ready to switch x and y. Okay, we need to get y out of the denominator. So let's multiply by y minus 2 on both sides. Okay, and then after we do that, we can divide by x and add 2. Interesting. So F inverse ends up being 1 over x plus 2. So the parent function, same parent function, but vertically shifted by 2 instead of a horizontal shift to the right 2. Very interesting. So the domain, and you can see it from the equation, would be negative infinity to 0, union 0 to infinity, and the range would be negative infinity to 2, union 2 to infinity. Oh, a piecewise function. We deal with it in the same way, but you're doing the process for each piece. It's sometimes helpful, I think, for determining 1-to-1 to think about the sketch of the graph. So I'm going to do that just to make sure. Just piecewise, I feel like you always have to think a little bit more about. Okay, so the graph will look like x squared when x is less than 0. So it'll look like that. And then negative x when x is greater than or equal to 0. So, oh no, I didn't mean to do that. So 0, 0 will end up getting filled in. Negative sloping line. Okay, so that's F. It would pass the horizontal line test and therefore is 1-to-1. Okay, it looks like the domain and the range would be all real numbers. But that's not super helpful for us for finding the equation. What would be even more helpful would be determining the range of each piece of the piecewise, because the domain and range of each piece is also going to switch. So the range, and that's another reason for thinking about graphing, the range was y greater than 0 for that first piece, and y less than or equal to 0 for that second piece. So focusing on the first piece here, I'm going to think about taking that equation, switching x and y. So I would have x equals to y squared. And then when I go to solve for y, we would want to have plus or minus the square root of x here, but like that wouldn't be 1-to-1, right? Like we can't, that wouldn't be a function. But we can think about the fact that the domain and the range should switch for this equation, right? So we know that x would be greater than 0 because I'm looking at the range of that piece, which was this part right here. Y greater than 0 is now going to be x greater than 0 for the inverse. And then the range will be y less than 0. That's thinking about the domain of that piece, which is now going to be the range. Well, for y to be less than 0, this is going to have to be the negative square root of x. So that piece will end up being that first piece of f inverse. I can start writing this out. Would be negative root x, comma, x greater than 0. And then switching x and y for the second piece, well, that's not very exciting, but domain and range switch, right? So this would be for x less than or equal to 0 and y greater than or equal to 0. So negative x, but for x less than or equal to 0. The overall domain and range is still all real numbers. I'm just going to put D and R. It would still be all real numbers. If we thought about the graph, well, negative root x would end up looking like this, right? Vertical reflection to root x for x greater than 0. It would be open circle at 0, 0. And then negative x for x greater than or equal to 0. So that point would get filled in. And that line, negative x, continues on. So that would be f inverse. And those graphs are symmetric about the line y equals to x. Okay, last example, right? Yep. Same type of thing. It's a piecewise function, so it could be helpful to us, especially for determining range if we think about the graph. Okay, 1 over x, when x is less than 0. Let's use blue. So that'll be, that'll be this bottom branch here in quadrant 3. And then root x when x is greater than or equal to 0. So it'll come out like this. And this does pass the horizontal line test. And is therefore a 1-to-1 function. Let's think domain, all real numbers. Range, all real numbers. But remember, it can be more helpful to think about the range, domain and range of each piece. So for x less than 0, the range would be y less than 0. Yep, negative infinity to 0. And then for the range of root x, that would be y greater than or equal to 0. Oh, that's not going to end up very interesting. Okay. So then for finding the inverse of the first piece, switching x and y, multiply by y on both sides of the equation here. So we'd have y times x equals to 1. And oh my goodness, we end up with y equals to 1 over x. And that's going to be for x less than 0, which, I mean, that piece, you maybe already saw it, would be symmetric about the line y equals to x. And the range would end up being the same as well. Okay, and then switching x and y for the second piece. Squaring both sides. And this will be for x greater than or equal to 0. I'm referencing the range. And then for y greater than or equal to 0 as well. So f inverse will be 1 over x. For x less than 0, and x squared for x greater than or equal to 0. So this would just overlap, and then that would be f inverse. And domain and range are also all real numbers. Okie dokie, this is section 1.5, one-to-one functions and inverse functions.